Hello, Internet. This is JF, and this is Introduction to Programming in ATS. This is Chapter 5, Parametric Polymorphism, the last chapter of the first book. So I'm just going to read this first paragraph to you. So, code sharing is of paramount importance in programming. In a typed programming language, we often encounter a situation where the same functionality is needed for values of different types. For instance, we may need to compute the length of a list, while the elements in the list can be characters, integers, strings, etc. Evidently, we want to avoid implementing a list length function for each element type, as it would probably be the worst form of code duplication. We want to implement one single function that can be applied to any list to compute the length of the list. This list length function parameterizes over the element type of a given list, hence parametric polymorphism. And it behaves uniformly regardless of what the element type is. This is a form of code sharing that is often referred to as parametric polymorphism, which should be distinguished from other forms of polymorphism, such as inheritance polymorphism and object-oriented programming. All right. So this chapter describes two ways to get parametric polymorphism. One of them, the one that it's emphasizing and that ATS itself emphasizes, is templates. ATS really wants to use templates for this. The other way is polymorphic functions. So, first part, function templates, and gives an example of two non-polymorphic functions. This is a function that swaps. It turns a charent into an int char, and here's another function that returns an int char into a charent. And you can see the logic of the function, like the actual code the function evaluates to, or like the actual code of the function is exactly the same, even though the types differ. And that would be the same for however many tuple types you create. They're like char string or string char or string or charent, like a tuple of two charents. Like the swap is exactly the same. But you have to repeat yourself without polymorphism. So it says, okay, here's a template. And with this template, you can pass parameters to the template, type parameters to the template that allow it to expand into the actual code. So you don't have to have a function for each kind of type you have. You just have one template, and you can instantiate that template with different types. So swap char and int, and it'll take your charents and turn into int chars. Or swap int char, and it'll take your int chars and turn them into charents using these tuple definitions up here. All right, so you notice that a function template is not a first class of value in ATS. So there's no expression that turns into a function template. And also that when you have templates, like when you put a template in your code, like it doesn't evaluate to anything. It doesn't appear in like a compilation result. It doesn't even appear in your C code. And it's only when you instantiate a template that you begin to see the actual code that's generated. And he points out that I think not here, but later on, that whereas a polymorphic function, you have one function and you have the function body, and that's it. So if you have a polymorphic list length, then you have one list length function, and the code that's generated is just in one place, and that's it, no matter how you call it. But with a template, then you can generate multiple instances of the template and have multiple actual functions, multiple actual code that gets called. So that can load up your code potentially. That's a concern that people have in C++. But it's not stupid. It's not going to have 10 identical versions of code because you use the same function with the same types 10 times. And here's also what he actually points out in this actual paragraph over here is that this is a type of unknown size. So it could be 128 bits. It could be 2 kilobytes. This is a type of whatever the machine size is. So 32 bits on a 32-bit architecture, 64 bits on a 64-bit architecture, which pretty much means a box type. And it doesn't include int. In particular, type does not include the int type. ATS allows that this might not be whatever the machine integer is, which is actually the case in some cases. Anyway. And he also points out two important syntax things, notes for syntax. You can have space here, and here, and here, and here, and possibly here as well. Yeah, it's fine with that. But you can't have space between these two angle brackets. And you can't have space between the function name and the opening angle bracket. So, no space there, and no space there. But otherwise, if you want it, you can have it. And he gives another example using, instead of having the parameters all together, he has two parameters separately. So instead of invoking it like char, comma, int, you can do char, int like that. Here's an example of a composition function that you should look into. It's interesting. There's a lot of there are actually a lot of examples in this chapter, but I'm not going to go over them. All right, and an important note here: function templates are type checked, but they're not compiled into code. So what I said earlier is basically what this one is about. All right, and now polymorphic functions. So he gave us a bunch of templates as ways to get polymorphism, but you can also use polymorphic functions. And an easy way to distinguish them is that if you've got a function, you've got some kind of fun or fn or whatever. Then you have some space here, and then you have the name of the function, like swapbox. You have some space here, and then you have your parameters of the function. So if this is going to be a template, then you can have your template parameters here. These are generally going to be t at yp for reasons that we'll go into later. And if it's not a template, if it's instead of polymorphic function, you're going to have parameters here. So it's generally going to be a typ for reasons we'll go into later. So again, it's just space templates here, and then polymorphic functions after the function name. And there's some other things that can appear on the right side as well, but this left side is just template arguments. So they're a little bit a little bit easy to see. All right, and he points out that you can, just as you call templates by passing like explicitly what types they are. So swap, and I'm invoking this template with a char and an int. You can also invoke polymorphic functions similarly. You just say, val y equals. If this were a polymorphic function, you can say, okay, I want you to take a box stir and a box int or something like that. And there's a little bit more. There's some more examples there. All right. And when calling a polymorphic function, we often omit passing static arguments explicitly and expect them to be synthesized by the compiler, as it does here in this last example. However, there are also occasions, which are not uncommon, where static arguments need to be supplied explicitly, as either they cannot be successfully synthesized or what is synthesized is not what you want. So here are a bunch of examples of synthesizing and telling the compiler to guess, basically. So this first example and the second example are exactly the same. You're saying, hey, figure it out, and hey, figure it out explicitly. And then you have, okay, figure out the first argument, but the second one is definitely a box stir. Here, figure out the second one, but the first one's a box stir. Here, figure out both. Here, both are box stirs. All right, now this is important. This is actually very important. I have seen two kinds of errors involving polymorphic functions that are extremely common in practice. The first kind is depicted in the following example. This is a swap box. This is a polymorphic function. You see the parameters come after the function name. And it's taking a t at yp, which is a type of unknown size. Now it says, notice that they sort for type variables a and b. So these a and b are type variables, and the sort is t at yp. It says this can pass type checking, but the compilation results in a compile time error. Actually, in my experience, I've never seen a compile time error. What I have seen is seg faults at runtime, and also seg faults that depend on like how you compile. So, like optimization level 3, it seems to run fine. Optimization level 1, you get a seg fault. So this is massively dangerous. So don't use polymorphic functions with types of unknown size, which includes int. Like again, int is a type of unknown sized ATS. You can only use it with box types. So it always has to be type like type. So that's error number 1. Error number 2 is sort of the reverse. This is a template that uses type like type instead of the @ sign. It says, strictly speaking, this isn't an error. This is totally fine. You can do this if you really want this. If you really want to do this. It says you probably don't really want to do this because this is more restrictive than you need to be. Like if this were t at yp, nothing would break. You would be able to apply swap box to more types. So it's unnecessarily restrictive. So this is unnecessarily restrictive, the second example, and this one is dangerously free. And hopefully in the future, like this will either be supported or it'll get a definite error. Like you don't want to have that in your code. And this is also, I think, why ATS emphasizes templates, because templates are more general. You can, like, polymorphic functions can't support this, but templates can support both kinds. And he says, okay, well, if there's a confusion, why do we have templates and polymorphic functions? Well, polymorphic functions show up later. So you don't really need them for any of the examples in this chapter, but they do show up with dependent types. And specifically, they show up when you have templates that produce polymorphic functions. All right. So another section, polymorphic data types. So code sharing also applies to data type declarations. For example, like we could have we could have a data type int list. And it can take and then this would be a list of nil or int list of nil. So int list nil. There's no reason you don't have to do it like this, but you can. Or an int list nil of int and then an int list. So you could do that. You can do an int list, and you can do a char list, and you have a string list. But you want polymorphism here as well, or code sharing here as well. So then you have a data type, and I think I have it, right here. So right here. So as a data type list 0, it takes as a parameter a type of unknown size, and has two constructors. One that's list 0 nil, which is defined by the type of unknown size. And then a second constructor, cons, which is refined the same way, and it takes as a parameter a value of that type, and a list 0 is refined by that type. So it turns into the same thing. So you have ints, you have a list cons int of some kind of int, and a list of ints. And he explains all that here. And of course, the reason, the fact that we have type, polymorphic data types is why we have polymorphic functions. There'd be no point in writing a list length function that can work on a list of any kind of type if there weren't the notion of what is a list of any kind of type. I'm going to use more examples. So, an option type. So option type, you can have a div op that returns option sum in the case where division is possible, or option none where it's not possible. And list last, where you can't get the last of nil, but you can get the last of any other kind of list. All right, and that is the entire rest of this chapter is examples, and I'm not going to do them. You can do them if you want. There are a lot of them, and they're pretty straightforward. So zipping, merge sort. This is an example of using define here. So I use define over here, and just for this what expression, because I didn't want to type cons, or even worse, list 0 cons. I never want to type that over and over again. So I used a terse syntax with define just for that one case. And to point out, I've said it before, this isn't C preprocessor, and it still isn't C preprocessor. But if you have an operator like this is a binary operator that ATS knows about, then you can define any kind of function as that, and then use it in a binary expression, and it'll take its parameters and give it to the function. So this is the first argument of list cons, and this is the entire rest of things, the second argument of list cons. And that just works. It's pretty straightforward. It works exactly how you'd expect. All right, and more examples. And all right, that is it. That's the video.